The RLC series circuit. So in this circuit we have our AC source and our load consists of a resistor, inductor and capacitor connected in series. So let's say that our reference direction for the current is like this, so that there is a voltage drop across R, across L and across C, which is equal to the voltage that we supply, which is delta V max sine omega t. Now, in the previous lectures, we have seen that while the resistor does not have any phase relationship between the current and the voltage across it, the inductor and capacitor do so. So there's going to be a non-zero phase between the current that flows in the circuit and the phase of the voltage source, the AC source. So what we're going to do is we will say that the current is going to be also sinusoidal. However, it will have a phase angle that is with respect to the AC source. So we can call this phase angle phi. It's going to be I max sine omega t minus phi. So phi is the phase angle between the current and the voltage. Okay, with that, if we look at the voltage across the resistor, it will be equal to the current times the resistance. The current is I max sine omega t minus phi times R. So this is Ohm's law. So we will obtain delta VR max, the maximum value of the voltage across the resistor, multiplied with sine omega t minus phi. So this will have the current across the resistor IR will be equal to I of t, and the voltage across the resistor will have the same phase relationship with respect to the current. Now, when we come to the inductor, we remember that in an inductor, the current lags voltage by an angle pi over 2. So that's what we have shown before. Okay, so what is the relationship between the current flowing through R, L, and C? So these currents are the same. That's a property of the series connection. So the current will be the same. IL will be I max sine omega t minus phi. But because the current lags voltage by an angle pi over 2, when we look at the voltage, we have to add an angle pi over 2. So I max times XL, inductive reactance, sine omega t plus pi over 2 minus phi. So sine omega t minus phi is the current, which lags the voltage by pi over 2. So the voltage leads the current by pi over 2. So plus pi over 2. If you look at the voltage across the capacitor, this time the current leads the voltage by pi over 2. So that's what we know from our analysis of the capacitor. And with that, the voltage must lag the current by pi over 2. So the current is I max sine omega t minus phi. Therefore, the voltage is I max xc sine omega t minus pi over 2 minus phi. Okay, so having written these phase relationships correctly between the voltages, we can see that we have a KVL loop here. So we can basically consider a Kirchhoff voltage law, so KVL loop, and we see that following this KVL, we're going to have delta VR plus delta VL plus delta VC equal to delta V, the voltage across the capacitor. But now we have a different phase relationship between these voltages. Therefore, this equation, the Kirchhoff voltage law equation, is really a phasor equation. And to indicate that we have these phase relationships between the voltages, I put a tilde underneath. So that basically shows that this is the phasor. Delta VR phasor plus delta VL phasor plus delta VC phasor must be equal to the delta phi phasor. Okay, so let's look at the phasor diagrams. Now for the resistor, it's going to have a current IR, which is I max sine omega t minus phi. So this is the angle with respect to the x-axis in the counterclockwise direction. So if I take the projection to the y-axis, I obtain the current. And for the voltage, I have I max times the resistance sine omega t minus phi. So it's going to have a larger magnitude, which is VR max. VR max is equal to I max times R, and it has the same phase relationship. If I look at the VL phasor, the voltage across the inductor, now first I have to put the current phasor here. The current phasor will be identical in both in all of these three circuit elements because of the series connection. It's IL max sine omega t minus 5, which is I max sine omega t minus 5. That's the current. So the magnitude is I max. So this magnitude, and this magnitude are the same. And its projection onto the y-axis is I max sine omega t minus phi as expected. Now, since in an inductor, current lags voltage by an angle pi over 2, voltage leads current. So if I put the current like this, then I have to put the voltage phasor with an angle pi over 2 in the counterclockwise direction with respect to the current. And this is going to have a maximum value, I max times the reactive inductance, which is XL. That's equal to omega L, as we have seen. Now, in the case of the capacitor, we have current leading the voltage by pi over 2. Therefore, voltage lags the current by pi over 2. So using the same current phasor here, I have to put the voltage phasor making an angle pi over 2 in the clockwise direction. That's the negative direction with respect to the current. Now, putting these three phasors together, as you can see, the voltage phasor for the inductor and voltage phasor of the capacitor are in opposite directions because the current phasors are the same. So I have a VL max minus VC max magnitude for this difference phasor. And then I have the voltage phasor for the AC source. That is this one, delta V max. So this is going to make an angle omega t minus phi plus phi, so an angle of omega t with respect to the x-axis because it has sine omega t. So omega t minus phi plus phi gives me omega t. So this total angle should be omega t. And the voltage phasor for the resistance was here, making an angle omega t minus phi. This is VR max. So looking at my KVL equation, you need to add these three phasors to get the total voltage phasor, which is the AC source voltage phasor. So if I do the vector addition of these two, you can see that I have this right triangle, VL max minus VC max, VR max, and the hypotenuse is equal to delta V max. So with that, I can write Pythagorean theorem, delta VR max square plus delta VL max minus delta VC max, parentheses square root is equal to delta V max. So now I can substitute what is delta VR max. It's I max times R using Ohm's law. Delta VL max is I max times XL, which is omega L, and delta VC max is I max times XC, which is 1 over omega C. So this squared plus this parenthesis squared square root, using Pythagorean theorem, I obtain delta V max. All right. So delta V max, therefore, is I max times square root, because I have I max square in all terms, square root of R square plus XL minus XC parenthesis square. So you can see that for this overall circuit, the RLC circuit, I have a factor that multiplies with I max to give me delta V max. So this factor was just inductive reactance in an inductor, capacitive reactance in a capacitor, or resistance in a resistor. But for the series connection, there is an effective frequency-dependent resistance that belongs to the circuit that we call the impedance of the circuit. So the impedance of the circuit is square root of R square plus XL minus XC parenthesis square. Why? So that we can write I max as delta V max over Z, which mimics Ohm's law. So Ohm's law we can use provided that we introduce the concept of impedance, which is a frequency-dependent resistance. Now, what is this phase angle phi? Now, I can look at this diagram again, the phasor diagram, that shows me that tangent phi is delta VL max minus delta VC max divided by VR max, so delta VR max. So from the phasor diagram, I can see that because this is I max times XL, this is I max times XC, this is I max times R, I max is cancelled. This is tangent inverse of XL minus XC over R. So what does that mean? If XL is greater than XC, the phase will be positive. So the current will be that if phi is positive, that means the current will be lagging behind the voltage, and the current lags behind the voltage in an inductor. Therefore, we can say that this load is more inductive. If XL is less than XC, then the phase will be negative. Then I will have the current minus phi becoming positive, so current leads voltage, which will be more capacitive load. So we can characterize the load as more inductive or more capacitive by looking at this, the sign of this phase angle. So if putting all of these together, I of t is equal to delta V max over Z, where Z is square root of R square plus XL, which is omega L, minus XC, which is minus 1 over omega C, parentheses squared, sine omega t minus phi, where phi is tangent inverse of omega L minus 1 over omega C over R. So basically we have solved the circuit, we have analyzed the circuit using phasors. Now, there's an alternative approach. Alternatively, we can define a complex impedance that's going to replace the phasor. So the complex impedance of a resistor is resistance R. It only has a real value. The complex impedance of an inductor is J omega L, where I use J is equal to square root minus 1, not I, because I stands for current, so we can use J not to confuse with current. And the complex impedance of the capacitor is 1 over J omega C. So why do we introduce these factors J's here? These are going to remind us of the phase relationship between the current and the voltage. Now, once you replace these impedances with complex impedances, you can put them here, R, J omega L, 1 over J omega C, and treat them as resistances in your circuit so that you will find the equivalent resistance or equivalent impedance as R plus J omega L minus 1 over J omega C. So you can see that this is going to be R plus J parentheses XL minus XC. Now, this complex impedance has a magnitude square root of R square plus XL minus XC square, and it has a phase tangent inverse of XL minus XC over R. So you can see that the phase that I was looking for and the impedance is, which is the magnitude of the complex impedance, I can easily obtain using these complex impedances for the circuit elements. Now, how does this remind me of the phase relationship? The complex voltage across the inductor will be the current multiplied by the complex impedance. So current multiplied by XL, which is omega L, e to the j pi over 2. So you can see that I'm introducing an additional pi over 2 angle here. So this is telling me voltage across an inductor leads the current by pi over 2. Or if you put this on the left hand side, e to the minus j pi over 2, you will see that current lags voltage. And similarly, we can for the 1 over j omega c, we can put e to the minus j pi over 2. And this is going to give us voltage lagging the current by pi over 2, or current leading the voltage by pi over 2. So this phase relationship can also be read from these complex impedances easily. Okay, so what I have said for the current across the current flowing through the inductor, it's VL over XL e to the minus j pi over 2 current lags voltage as expected, and IC is VC over XC e to the j pi over 2 current leads voltage as expected. So this matches our previous phasor analysis. So we have two approaches. We can use complex impedances or phasors to figure out the current voltage phase relationship. Let's look at an example. A series RLC circuit has a resistance of 425 ohms, inductance 1.25 henries, and capacitance 3.5 microfarads. It is connected to an AC source with a frequency 60 Hz and maximum value amplitude 150 volts. Part A, determine the inductive reactance, the capacitive reactance, and the impedance of the circuit. So the resistance is 425 ohms. The inductance is 1.25 henries. Capacitance is 3.50 microfarads. The frequency is 60 Hz. And we know delta V max of our AC source to be 150 volts. Now, we can look at the circuit. We have the resistor, inductor, and capacitor connected in series to this AC source, and we have the same situation as before. So in order to calculate these capacitive reactance, inductive reactance, and the impedance of the circuit, first I'm going to use the complex impedance method. In the complex impedance method, this resistance is basically replaced by R, L is J omega L, and C is 1 over J omega C. Now, treating these as frequency-dependent resistances, I can write the complex impedance of the circuit as R plus J omega L plus 1 over J omega C, complex impedance of the capacitor. And once again, what I'm calling J is square root of minus 1. So this is in the form R plus J XL minus XC. So what I'm calling XL, inductive reactance, is equal to omega times L, which is 2 pi 60 angular frequency multiplied by the inductance 1.25 henries. This gives us for inductive reactance 471 ohms. And for the capacitive reactance XC, which is 1 over omega C, that's the magnitude of complex impedance of the reactance. This is 2 pi 60 times capacitance 3.5 microfarads, 10 to minus 6 farads to the power minus 1. And this gives us a capacitive reactance of 758 ohms. Now, the impedance of the circuit, Z, is basically equal to the magnitude of the complex impedance. So this will be R square plus XL minus XC square. So that's the magnitude of this quantity, square root. So this will give us 425 squared plus 471 minus 758 parentheses squared square root, and that will give us the impedance of the circuit to be 513 ohms. Now, second method using phasors. Okay, so let's look at how we can solve this problem using phasors. So I'm going to show all the voltage phasors in a single phasor diagram for the inductor, the capacitor, and the resistor. So let's show the voltage across the inductor by VL. Now the current, let's say in this phasor diagram, has zero phase at this moment in time. So I'm going to have the voltage phasor VR max for the current, and this is the current phasor I max. Now the current flowing through the resistor, the capacitor, and inductor and capacitor, they are the same. So for the inductor, because the the voltage leads current by pi over 2, or current lags voltage by pi over 2, I'm going to put the voltage phasor here, and it's going to have a magnitude VL max. So this is my angle pi over 2. And for the capacitor, I have to put the voltage in the opposing direction. So this is going to have a magnitude VC max. And once again, lagging the current by pi over 2, our current leads the voltage across the capacitor by pi over 2. Now, if we put all of these together in a single phasor diagram, by performing the addition of the voltage phasors, I'm going to get basically a resultant phasor for inductor and capacitor of magnitude VL max minus VC max, pointing up in the up direction. And then I have the voltage phasor here for the resistor. This is VR max. And in my KVL loop, I can see that these voltages should add up to delta V. So when I perform the addition of these phasors, I'm going to obtain a phasor that's going to make an angle phi with respect to the current, and it will have a magnitude delta V max. So you can see that the current is basically lagging behind the AC voltage by an angle phi here. So it's like drawing these at time t equals to 0. So I have I max sine omega t, so that the phase angle is 0. So it's going to be sine omega t minus phi, but t is 0, so it's going to be just minus phi. So it's basically lagging this voltage phasor by an angle phi. Okay, so the same analysis, basically, it shows me the magnitude from this phasor. I can read the delta V max square is VL max square minus VC max, VL max minus VC max parenthesis square plus VR max square, which will give me exactly the same result for the impedance. Now, let's move on to part B. Part B asks me, find the maximum current in the circuit. Now, the maximum voltage, delta V max, is related to the maximum current in the circuit. Once I know the impedance of the circuit, I max times Z. Remember, this behaves like Ohm's law. So we have I max is equal to 150 divided by 513. 150 volts was the maximum voltage. 513 ohms is the impedance of the circuit that I calculated. So this gives me a maximum current in the circuit as 0.293 amps. Part C, find the phase angle between the current and voltage. Okay, the phase angle, phi, as you can see from the phasor diagram, is tangent inverse of VL max VC minus VC max divided by VR max, which is XL minus XC over R, or that's the phase angle of this complex impedance, XL minus XC over R, tangent inverse. So tangent inverse of XL minus XC over R is what I'm looking for here. That is equal to tangent inverse of, now let's plug in the numbers. XL was 471 ohms, XC was 758 ohms. The resistance is 425 ohms. So this gives me an angle phi of minus 34 degrees. It's going to be a negative number. So phi will be minus 34 degrees. So instead of being in the counterclockwise direction, this is actually in the clockwise direction. So the current is basically leading the voltage instead of lagging the voltage. So that's the end result. Part D, find the maximum voltage across each element. And now that's very easy. For the resistor VR max or delta VR max, we can say it's going to be I max multiplied by the resistance R. Since I know this is 0.293 times 425, this will give me a VR max of 124 volts. That will be the maximum voltage that will appear across the resistor. What is the maximum voltage across the inductor? VL max, it's I max times its impedance, which is a reactive inductance, XL. So this is 0.293 amps multiplied with 471 ohms. That gives us a maximum voltage, VL max, 138 volts. And we can calculate the maximum voltage across the capacitor, VC max, as I max multiplied with XC. This is 0.293 amps times 758 volts. The maximum voltage across the capacitor will be 222 volts. Okay, so let's look at part E. What replacement value of L should an engineer analyzing the circuit choose such that the current leads the applied voltage by 30 degrees rather than 34 degrees? All other values in the circuit stay the same. So we want to change the phase angle between the current and the voltage. So tangent of the angle phi, which is tangent of minus 30, will be equal to XL minus XC over R. And this is minus 0.577. Now XL will change, XC will stay the same, 758. It will be equal to minus 0.577 times R, 425 ohms. So XL, which is omega L, 2 pi 60 L, will be equal to 758 minus 0.577 times 425, and this will give us an inductance of 1.36 henries. So to change the phase angle from minus 34 to minus 30, I have to change the inductance from 1.25 to 1.36. Okay, so in this circuit, I observe that the capacitive reactance XC is greater than the inductive reactance XL. So this circuit is more capacitive. As a result, current leads voltage. Current leads the voltage of the AC source. So what we have seen in this analysis is that in an AC circuit, when adding currents or voltages, we need to take into account their phase relationships. So therefore, basically, we need to add phasors. So we need to take into account their phase relationships, and we do so by using phasors, or we can use this complex impedance analysis. Okay, so in summary, we have analyzed an RLC series circuit. We have an AC source, delta V max sine omega t. The current in the circuit is time dependent, and it has a phase relationship with the voltage, sine omega t minus phi, where I call phi the phase angle. Now, when I look at each element in the circuit for the resistor, the current and voltage, current flowing through the resistor and voltage across the resistor have the same phase, so there is no change. When I look at the inductor, since the current flowing through the resistor, inductor, and capacitor will be the same, the IL stays the same, I max sine omega t minus phi, but delta VL, I have to multiply I max with XL to get delta V max, and as for the phase relationship, current lags voltage, current flowing through an inductor lags the voltage across the inductor by an angle pi over 2, therefore voltage leads the current by pi over 2. So I know the phase of the current is omega t minus phi, therefore the phase of the voltage is omega t minus phi plus pi over 2. And for the capacitor, likewise, it will be minus pi over 2 because current leads voltage across a capacitor by pi over 2. When I write the KVL equation, Kirchhoff voltage law, in this circuit, delta VR plus delta VL plus delta VC must be equal to delta V. And in order to indicate that this is a phasor equation, I can put these tildes underneath the deltas. And when I do this vector addition very carefully here, I have I omega t minus phi. So this is the current phasor. The voltage phasor is in phase. So it's going to be VR max, which is R times I max. So this has a value R times I max. It has the same phase. And for the inductor, I have the current lags the voltage by pi over 2, same current phasor, but the voltage phasor is here, and this phasor will have a magnitude XL times I max. And for the capacitor, current leads voltage by pi over 2, so the voltage has to be with an angle minus pi over 2 with respect to current, and this will be XC times I max. So when I perform the vector addition, VL max minus VC max, because they're in opposing directions, and VR max is here, making an angle omega t minus phi with the x-axis, I obtain the total phasor delta V max, making an angle omega t with the x-axis, or phi with respect to the voltage across the resistor. So you can see that by performing this vector addition, I can see the magnitude of the voltage phasor as square root delta VR max square plus delta VL max minus delta VC max parenthesis square, which is I max R parenthesis squared plus I max XL minus I max XC parenthesis square, which tells me that the impedance of the circuit is square root of R square plus XL minus XC square. Maximum current is delta V max over Z, the impedance of the circuit, and the phase phi can be read from this right triangle as tangent inverse of XL minus XC over R. Positive phase, more inductive; negative phase, more capacitive. And alternative method, we can define R, J omega L, and 1 over J omega C as the complex impedances. Now, the complex number that we obtain by addition of circuit resistances connected in series, these are frequency-dependent complex resistances, we obtain the complex impedance of the circuit, which has a magnitude equal to the impedance of the circuit, and phase, which is equal to the phase angle between the current and the voltage. Okay, and we have applied these results to a numerical circuit analysis, and we can calculate XL as omega L, XC as 1 over omega C, and the magnitude of the complex impedance Z, or we can look at the phasors and perform the same analysis. And delta V max will be I max times Z. That's the whole idea. We can replace all of these elements with a single impedance Z, frequency dependent resistance. The phase angle we can calculate tangent inverse XL minus XC over R. The voltage across each element has a maximum value, the maximum current multiplied by the impedance of that element, R for resistor, XL for inductor, XC for capacitor, which is omega L for inductor, 1 over omega C for capacitor. And we can substitute the numbers to calculate the phase angle, but if we want to change the phase angle from minus 34 to minus 30, because the problem statement says the current leads the voltage by 30 rather than 34, is that the case? So this phi angle that we have here is basically going to be negative. So that means delta V max will have an angle phi here. The current is here, so it's going to be a negative phi, which means the voltage will come down, so the current will be leading the voltage, right? So we want to lead with a smaller angle, so we can replace the tangent phi with tangent of minus 30 and calculate the new XL value. The new XL value will give us the inductance using 2 pi f times L. And since I have XC greater than XL in this circuit, this is more capacitive and current is leading the voltage. And finally, basically the point of all of this is that in an AC circuit, we have to be careful when adding currents or voltages using Kirchhoff voltage law or current law, because we need to take into account their phase relationships, i.e. all of the operations that we do here are phasor operations, which can also be easily performed using complex impedances as an alternative.